Okay, well, if there are no other questions, we'll move on to our final topic of the day, which is sound. And this isn't too crazy, and it's pretty related to what we covered before with light and optics, because sound is a wave. Okay, let's move on. So, at a general sense, just like light, sound is a wave and has very much the same properties as any wave, as a light wave, as a sine wave, cosine wave, right? Has an amplitude. It has a wavelength from here to here. It has, or here to here as well, has a frequency f, which is how many wavelengths per second, right? Or per period, per time period. These two don't know rarefaction and compression. Compression is this. It refers to this diagram, right? This blotted diagram. Compression is specifically this, where this line is in the middle. Rarefaction is this, where there's no line in the middle, but you really don't have to know that. Okay. And then there's also velocity of propagation, right? Velocity, speed of a sound wave. Speed of sound wave is usually in air 300 meters per second, right? V right here. But yeah, they'll give you if it's anything else, and they'll usually give you even if it is 300, just to be clear. So some general properties. Again, remember that wavelength equals V over frequency from when we covered light waves. Speed of sound in air is usually given as 300 meters per second. If it's different, they'll give it to you. Even if it is this, they'll probably give it to you anyway, so you don't have to memorize it. In a sound wave, amplitude usually determines loudness. So remember in light waves, frequency determined what color the light was, or if it was beyond the color spectrum, what type of light wave it is in the EM spectrum. In a sound wave, amplitude determines loudness. So large amplitude, very loud sound, low amplitude, quiet sound. Whereas frequency of wavelength determine pitch, right? High pitch, low pitch is high frequency, low frequency, right? And sometimes things get so high frequency, again, you can't hear them. It's beyond our, it's similar to visible light spectrum. It gets beyond our audible hearing spectrum, I guess. Another thing which we didn't really cover in light, but is important here is in phase and out of phase, deconstructive and constructive interference. If two waves are perfectly in phase, they will be constructive. If two waves are perfectly out of phase, they'll be perfectly destructive. Here's what this means, right? And sorry, let me annotate. And so constructive, if you can see, when you add two waves together, you can either get a bigger wave or you can get no wave at all. And these are the two extremes, right? Some things can be somewhat constructive, somewhat destructive. They can be, it's a spectrum, right? These are just the two extremes of the spectrum. Perfectly constructive, perfectly destructive. And let's look what that is. So you notice how there's these peaks and then these troughs, right? And when in these two waves, the peaks of the two waves coincide, right? And the troughs coincide. So when you add these together, you get two peaks at the same point. You can just get a really bigger peak, right? It's kind of like when we talked about the action potentials, right? Even in actually in muscles, when you have multiple action potentials like going together, it creates a bigger muscle contraction. But similar to that, constructive interference, multiple waves with peaks at the same place will create constructive interference. So it's just a bigger peak or a bigger trough in this case here, the bottom. And then again, it'll be like that. Whereas in perfectly destructive interference, you notice it's the opposite. This has a peak here and a trough here in the same spot, right? Same spot, there's a peak here and in this wave and a trough here in this wave. Assuming that the peak and the trough are the same amplitude, these two waves have the same amplitude, they'll perfectly cancel out. Just like with forces, if you have a force going up and a force going down, as long as they're the same magnitude, the forces will perfectly cancel out and you'll have no force. Just like that here, you'll have no peak, no trough, anything. And then same thing here, cancels out. And if you notice at all points, it'll perfectly cancel out. At all, yeah, exactly. All right. I wanted to mention a couple of things. So constructive interference doesn't necessarily have to be from source. So for example, if you had a speaker right here at this location, and then a speaker right here at this location, right? And they were creating these waves. This speaker would create this wave, this blue wave, and this speaker would create this yellow wave, and assume this is exactly what it would look like, right? In this region where there's only one speaker, you would hear this wave only. And then once you reach this point, this wave would be created, and assuming it's like right back to back, there's no like vertical distance between them, right? They're back to back. They would have constructive interference, and then from this point onwards, you would have like this wave, right? So up until this point, it would be like this, and then once you reach this second speaker, it would be constructive interference. Theoretically, if you did this at every single location right here, and added another speaker, another speaker, another speaker, and then you had a person standing right here, when they would hear something like really, really loud, like amplified many, many times over. And believe that's used in some like speaker technology, right? To have constructive interference, to make things louder. And some like speakerphones and stuff. And I know that if destructive interference is used in noise canceling headphones, when the headphones receive a certain wave or a certain wave of sound, they'll create a perfectly destructive wave. They'll try and create a perfectly destructive wave to cancel out, and the result will be no sound, right? And that's how noise canceling headphones work. Next, we want to move on to the Doppler effect, right? So the Doppler effect states that when a wave, specifically a sound wave, is moving towards or away from an object, if the object itself is also moving, the frequency heard by the object is different than the frequency of the sound actually emitted. Maybe a little bit confusing, but it's basically just states that as something is moving away from you or towards you, something that emits sound, right? Like a siren or anything like that, anything that emits sound, or even a person talking, as it's moving away from or towards you, the frequency of the sound that you actually hear is different than the frequency of the sound that is actually being released by the object, right? It's slightly altered, right? And I can show a diagram of this. So if you had like something that was just standing still, this is what kind of waves you would emit. This is pretend this is like frequency, right? And this is an observer, like a listener, like a human, right? This is what the frequency would sound like. If you had this exact same trumpet, except it was on a car that was moving towards you, the frequency would be much higher. If you had this on a car that was moving away from you, it would be the frequency would be much lower, and it would be, and you would hear it. It's much lower. The frequency actually emitted by the trumpet is not changing. So it's the same, and that's why I don't really exactly like this picture. The actual frequency is the same, right? That the trumpet emits, it's the same every time. What you hear is different, right? What the person hears is different. And the same thing applies to if the object is standing still. So if the trumpet was standing still, but you were moving towards the trumpet as it was making a sound, or you were moving away from the trumpet as it was making a sound, also it would change the frequency that you hear. But I do want to stress that the actual frequency emitted doesn't change, just what you hear changes. It's relative to the observer. Okay, next I want to move on to the actual equation for this, because this is like the most important part of Doppler effect will be the equation. So F prime is the frequency heard by the frequency heard by the object. I wrote object here, but it should be like listener or observer or something like that, right? Like a person or whatever, any kind of like anything that's hearing. F0, which is the initial frequency emitted by the source, is the actual frequency. And then if you want to think of it, this whole thing, I like to think of it as like a ratio, right? So you take the original sound and then you multiply by some ratio, and then you get your altered sound, right? And this whole thing is the ratio. As you can see here, there's these V with no subscript. This is just the speed of sound, right? Usually, again, it's 300 meters per second. They'll give it to you, right? It's the actual speed of the sound wave. This, and then you notice here it's plus minus, whereas here it's minus plus, right? That'll come into in a bit, based on direction. So sometimes in some textbooks and in some books, you may just see plus plus or plus minus or something like that, right? Just one sign on the top, one sign on the bottom. Whereas in others, you may see it like this. I prefer this way just because it makes it easier. What that means if you only have one sign is it means you have to know when to make a velocity positive or negative, right? This v0 is the velocity of the object, and this vs is the velocity of the source, which is the source of the sound. So you would have to know whether, if you just used one sign, you'd have to know whether to make a velocity positive or negative based on the direction it's moving away or towards you. I prefer this way because there's an easy way to remember it. Towards is top. So if you're moving, if something is moving towards, you use the top sign. For this, you use plus because it's the top sign. Here you use minus because that's the top sign. If it's moving away, you use the bottom sign, right? In this case, minus, this case, plus, right? When I say towards and away, for example, this is talking about the object or the listener, right? The actual listener. If the listener is moving towards the source of the sound, you would use plus. If the listener is moving away from the sound, you use the bottom of minus. If the, and VS on the bottom here stands for source, right? If the source is moving towards the listener, you would use the top. If the source is moving away from the listener, you would use the bottom. Right? And again, you could use, for this one, you could be using the bottom one because it's moving away. And for this one, you could be using the top one because you're moving towards, right? And those are separate. Okay, last poll question of the day. Okay, so it seems that most people have picked choice C, which is correct, right? And I'm happy to see that. So two jets are flying together, one with a siren and the other with a receiver, which is some kind of listening device. As the speed of the siren jet flying away from the receiver jet increases, what happens to the distance between adjacent peaks of the wave as heard by the receiver? First thing you have to notice is what are they actually asking for? What happens to the distance between adjacent peaks of the wave as heard by the receiver? They're asking for f prime, right? The distance between, or they're asking for a variation of frequency, right? So the distance between peaks, the frequency is the distance between peaks, right? But if, for example, the distance between peaks increases, that means the frequency is actually decreasing, right? Okay. Let's get to the actual equation. So it's f0, but we're not really particularly interested in that. Like I mentioned, it's a ratio, so we can actually just ignore this and just do v plus minus, minus plus, and on the top is object, and then here is the source, right? As the speed of the siren jet flying away from the receiver jet increases, so the speed of the source is increasing away. Away means the bottom, so we're using the plus sign, right? And as this speed increases, what happens to this? Well, causing, you know that this would be v either plus minus, we don't care, plus minus VO. It actually doesn't matter, right? Whereas this is v plus vs, right? As this increases, as vs increases, the whole bottom, the denominator will increase. If the denominator increases, that means this number as a whole, right? If you want to think about this whole thing as a number, will decrease, because if the denominator is getting bigger, that means the whole thing is getting smaller, right? It's like how you're going from 1/5 to 1/6 to 1/10 to 100. As the denominator is increasing, the whole number is actually getting smaller, right? So that means this is getting smaller. If this is getting smaller, that means f prime is also getting smaller because they're proportional. If f prime is getting smaller, that means the frequency is decreasing. If the frequency is decreasing, the distance between the peaks is increasing, right? Because the distance between peaks is what frequency measures. low distance between the peaks, that means there's a lot of peaks, is frequency. And distance between adjacent peaks is very similar to wavelength, right? So it's actually asking for wavelength. You know, wavelength and frequency are inversely proportional. As one increases, the other decreases. So if wavelength's increasing, if frequency is decreasing, wavelength is increasing, the answer is C.